Okay. Hello, everyone. Welcome back to our seminar. Happy Valentine's Day. Today, to celebrate this nice day, we have with us Jacopo Emmenegger. I'm sorry about you. I cannot pronounce it. Emmenegger. And he's going to tell us things about Lawvere doctrines. So I'm really very looking forward to this seminar. So please.
So they have doctrine of law, if I understand well.
Yes, it's Lawvere. Yes.
Law here, exactly.
Yeah, thanks a lot for having me. It's good to be here, and I'm really sorry that I had to leave sooner than I planned. But I'm still very happy that I'm able to give the seminar. All right, so let's begin with a question, and the question is the one in the title. So, what is a logical theory? For those of you who were present yesterday morning, you already got a taste of where I want to go with this question. Yeah, there are a few possible answers that one can give. Sorry, I would like to do this. Right. Oops. And so if you're a model theorist, you might say that it's the set of sentences that are true or valid in some class of structures. If you're a proof theorist, you might say that it's a set of sentences closed under derivation with respect to some calculus for deductions. You might even want to say that it's just a set of axioms. I mean, then you close it by deduction. And somehow there is not a unified notion of what could be a logical theory that would then somehow collect all these possible answers into a single one.
Sorry, what in logical theory, logic is as essential? If I put instead of logical, mathematical, it would be
I'm thinking, I don't know, that you could speak of type theories, for example, which are theories, but not. Somehow they speak about types and not about propositions. So maybe the difference is also a bit blurry, but I don't want to delve too much into these details right now. So what I will speak today about is the answer that was proposed by William Lawvere, who proposed this notion of doctrine as a possible intrinsic definition of what is a logical theory. If you want, in the same way as the modern definition of group is an intrinsic definition that does not rely on a specific presentation or on some other kind of context. Okay, so let's look at the first proposal by Lawvere of what is a logical theory. It says it's just a small category. This is the idea that appears in his PhD thesis, it's Functorial Semantics of Algebraic Theories, in 1963. And so the theories is actually concerned with algebraic theories, which are a very basic one, just in the fragment with finite conjunctions and equality. And this corresponds to small categories with finite products. But then if you add logical structure, then you can see that also on the categorical side, you can somehow keep track of the additional connectives and quantifiers that you add to the logic. So one nice thing of this approach also is that you get the notion of model and morphisms of models as standard categorical concepts. So a model becomes just a functor into the category of sets, or set theoretic model. Then at this point, you realize that you can replace set with another category and take models somewhere else. Typically, when you take an elementary topos or a grouping topos, which somehow look like set, but they're a bit more general. And then you get automatically also a notion of morphism of models, which is natural transformation. So this was the first idea. but then he refined this idea a bit a few years later in a series of papers that you see at the bottom of the slides. The first one is from 1969, 6 years later. And here it says that a logical theory is it's not quite a small category, it's rather a small doctrine. So a doctrine, it says, is a family of posets indexed on a category. So the idea is that in this way, and I mean, I will show you the precise definition, of course, but just intuition is that the base category, so the category you're indexing over, is where the language lives. And the family of posets instead is where the logic lives. So somehow this allows to separate these two aspects and treat them in a bit more clear way. I mean, all the rest remain virtually the same, mutatis mutandis. The more connectives and structure you add on the logic side, you have corresponding notions on doctrines. And the model is a morphism, and then you have a notion of a two-cell between these morphisms, which gives rise to a notion of morphism of models.
Sorry, I have a question here. So you say the logical theory is a small doctrine.
Mm-hmm.
You can also say that a small doctrine is a logical theory. So this is a univocal definition, or is simply a description of a theory, but there are a lot of other things that are not theories that can be described in the same way. Because in this way, we do not explain to the question, we do not answer to the question, what is a theory? We simply say that the theory is something of this sort, but the question, what is a theory, is still open to discussion, because from here, I don't know what is a theory.
Right. So maybe the question is rather, how do we define a logical theory, rather than what is a logical theory?
No, because...
but I mean,
so I would be happy.
The idea is that a small doctrine is a logical theory. So
there is nothing else that is.
That's right.
It is more doctrine that is not a logical theory.
Right. So the idea precisely is that the notion of Lawvere's doctrines is a sort of a specification, an algebraic specification of what a logical theory is. Then you can come up with actual instances of doctrines, which can come from model theory, from proof theory, model logic, so on and so forth. And in this way you construct examples, instances of the notion of doctrine. But this notion of doctrine is a sort of umbrella where you can somehow comprise all these notions. And so algebraic aspect means several things, actually. So entails also several things. First of all, Lawvere realized that logical connectives and quantifiers and also non-logical kind of structures that you can put on a logic, they can be expressed by adjunctions between the fibers of the posets that I mentioned, or between these fibers and the base category. And yeah, as I already mentioned, you get models as morphisms. And a second consequence of the algebraic aspect is that the categorical notion of completion, which is formally given by adjunctions, provide a very structured way to get conservativity results for these logical theories, for extensions of logical theories under various kind of connectives, quantifiers, and other principles like, I don't know, comprehensions, or rather extensional equality. Right. And in particular, then each such bi-adjunction will give rise to a two-monad or a two-comonad, according to the kind of thing you have at disposal. And then these kind of structured doctrines can be described as algebras or co-algebras for this kind of guys. So then mention some applications of these facts to categorical logic, and also a bit outside of it. And I will conclude with some telling you some current work in progress I have with several people. Okay, so maybe it's time to look at the definition of a doctrine. And that's it. So a doctrine is a category C with finite products together with a functor from the opposite of this category into the category of posets. So what does this mean? Let's unfold it a bit. We have this functor P that maps each object of the category to a poset, P of A, and each arrow F to a monotone function that goes in the opposite direction. This is why we have an op here for the category C. And usually this the action of this F is called reindexing along F.
Here C is small.
Here it's not necessarily small. It's not a small doctrine. It's a doctrine.
That's a doctrine.
A small doctrine is small when C is small. Okay, so let's look at some examples. Let's begin with what I said before. If you have a logical theory in some sense, you can construct a doctrine in this sense, which is usually called the syntactic doctrine, and is described in this way. So the base category is given by context and so-called context morphisms. So a context is a list of sorted variables. They must be distinct, and each one must come together with its sort. And then the arrows of these categories, they are a list of terms, like this one, T1, Tn, where each single term is of the right sort on the right-hand side. And it contains variables that appear in the context on the left-hand side. Okay. And now the identity of this category on some object. Here is a context of length 1, but you can figure out how the identity on an arbitrary context is. It's just the projection of all the variables. It's the list of terms that does nothing. And then for in order to compose two such morphisms of context, you use the notion of substitution of one term into another, basically.
So I'm really ignorant. What is a context again?
A context is a list of variables,
Okay.
that must be distinct, and they must come together with their sort. So if your theory is single sorted, you just take a list of distinct variables. All right, so let's.
What a variable correspond in the theory?
This is pure syntax. This is
Syntax.
pure syntax.
No, I want to mean, if there is for any variable in the theory, there is a variable that is not, or there is one variable for, that's not clear to me.
I mean, usually you assume that you have countable many variables available.
Yeah.
And I mean, in this case, you can say that for each sort, you have countably many variables wherever it's possible. So you can keep them distinct no matter the length of the counters. Okay, so other questions on the base category?
With this definition, there is a technicality
Mhm.
problem, which is that if you know what the terms are and you know, then you do not know what the codomain is.
I mean, for me, the terms are terms in context and are sorted.
Yes, terms in context, they are sorted, but if you know T1, T2, Tn,
Yep.
you do not know what the codomain is. You do not know which variables form the codomain.
Oh, yeah, no, right. So that's just a shorthand.
Yeah.
For me, a term is the expression that I've written below.
The term is domain, that, codomain.
Exactly. Yeah. So by a term in context, I mean a context, a sequence of
Yeah.
function symbols and variables, and then a sort.
I see.
So this is a sorted term in context.
We can discuss this later.
Okay. Then So the fibers
So,
that
sorry, different, so for first order theories, no problem. Second order theory is treated as a two-sorted theory,
uh,
but there is a difference between order and sorts.
between order.
So I can take a second
you-
order theory as a first
No,
order
I mean
theory.
in order
with
in order
two-sorted
to,
first order theory.
yeah, no.
Syntactically speaking, does make no difference. The difference is only semantical.
Right. So this is basically works for first order theories.
Okay.
You can encode some form of higher order logic if you have additional structure in the same way that happens in an elementary topos, for example, where you have a collection of your proposition, and you basically you assume that you can quantify over.
Yes, but I think so
things in the
far
collection.
we are not semantic here. There is no difference between first and second order. Second order is simply a bit sort of first order.
Yeah, I mean, there are no quantifiers either for the moment, so it's not even first order, actually. We need to add
The
structure
difference
in order
between
to
first
speak
and
of this
second
kind of
order
stuff.
does not depend on the quantifier, depend on where the variable range are. If we have a variable range on a domain, and another variable range on the subset of the set of the domain, this is second order, even if you have no quantifier.
Then maybe you can accommodate them here. Yeah.
So, but if this is a semantical definition, it depends on the way in which you take the model of the theory. If you have without pure semantic, there is no difference really between first and second order. You have one sorted as the element, another sorted as the concept, another sorted as the relation.
Then it works.
And then you can all put on first order and simply to have a second order.
Yeah, actually, I would be interested in discussing this a bit more because I'm not very familiar with formula of higher order logic. It would be nice to understand how they fit into this also. Okay, but let's get to the logic. This was just the language. So the fibers are the Lindemann-Tarski algebras of your formulas, which again, I work with formulas in context. So each formula comes with a list of variables, which are precisely the variables that appear in that formula. And then the order of this poset is given by the entailment relation of your theory. And the reindexing, the action of the arrows of the base category on the elements of the posets, in this case amounts to the action of a list of terms on equivalence class of formulas. And this action is given by the substitution of the terms into the formula. And this should make it clear why we want the indexing to go in the opposite direction with respect to the underlying arrow, because the substitution goes in the other way. So if the terms T1, Tm have three variables in that are y1, ym, then we plug them into a formula. That formula goes from variables in the x's to variables in the y's.
Excuse me, maybe I'm wrong, but I see some kind of a Galois connection.
There is not yet, but
It
there
will,
will come. Yeah. I mean, a Galois connection is a special case of an adjunction.
Okay.
So yes, these are the things I was talking about before. Okay, and there is a quite an important kind of reindexing, which is this one, which is not quite the same X that was the identity from before. This is rather a projection. And the indexing of this is usually called weakening. So you're taking a formula which only has this variable, and you're thinking of it as if it had two variables, but it actually only has this one. And recognizing these kind of transformations is essential in order to describe the quantifiers using adjunctions. This was the main insight of Lawvere. Okay. Questions about this example? Otherwise, we look at some more. So on the category of sets, oh yeah, sorry, I forgot to say. Usually this one is small. I mean, your context and terms.
Where is the exact definition of small?
Small in the well, it's relative to your meta theory. So assume you work in a set theory like. I don't know.
Just
If you have-
avoiding
if you have-
classes.
if you work in ZFC, you need some
avoiding-
inaccessible cardinals in order to distinguish between large and small. You can speak about classes.
Yeah,
If
just
you work in a
avoiding
set
classes,
theory,
right? Just avoiding classes, then you get to think more.
Small, yeah, I mean, but it's not,
But
it's
if
not
set is
necessary.
small,
to-
a set is small and the class is not small,
Exactly.
or a set is countable and the class is.
No. A set is small, a class is not.
So small means that the objects form.
Sorry?
Small means that the objects of the category form a set rather than a.
But this can also be given relative
And the arrows, yeah.
to
Yeah.
a
So
Rogers
they are-
universe.
They are very big, small.
Yeah.
Oh, yeah, definitely.
Oh, yeah. No
You have a lot of degrees of smallness. I mean, that depends on the kind of assumptions you want
Because
to
there are,
make in theory.
in logical mathematics, there are contexts in which you use small to indicate just.
Universe is close to.
Oh, no, sorry, no. I didn't know that. No, this means not a class, not a proper class.
Cartesian
I mean, it's just a technical one, right? You could have to.
Anyway, so on the category of sets, we can take
But
power
then,
sets.
so this is what small means.
One object.
Your theory of doctrine require as a subjacent theory. So without the theory, you do nothing, because you don't know what does it mean small.
Yeah.
So it's a theory. So
But,
in order to understand
I mean,
what
you-
is a theory, I need a theory.
Of course, yes.
This is always the issue.
I mean,
So the
no way out of
small,
this, I think.
small is always understood with respect to some ambient meta theory. When people in category theory use the word small, this is what they mean.
But, I mean, also for doing set theory, you need meta theory.
No,
There is no.
Well, I mean, one way to do this is you have ZFC plus a countable chain of Grothendieck
yeah.
universes, and those give you like level 0 you can call small, level 1 you can call large.
but if I have say theory, I have all mathematics, so I need nothing else. Why? If I have say
No,
theory,
the point is that this is a way to structure
I think
the,
that Peter
the thing
would
that we know.
agree with me.
I mean, you can do this in plain ZFC without speaking of doctrines. The point is not to say that this is not possible, but rather that it's convenient to organize our knowledge using this kind of gadgets. Right? Okay, so I mean, I try to give some evidence to this claim, right? Okay, so we have the power sets. This should be familiar to most of you, I think. The reindexing in that case is given by counter image, not direct image. Must go the opposite. Then if you have a poset, you can look at functions into that poset from a set. This also gives rise to a doctrine. And in fact, the power set doctrine is a special case where H is 2. And for a category with finite limits, you can take its subobjects. And again, 1 is also a special case of 3 when you take subobjects in the category of sets.
What is H?
It's a poset.
H is a poset.
Yeah. And there is a slightly less known kind of doctrine, which is the weak subobject doctrine, also called the doctrine of variations, after Marco Grandes, where the posets is not the subobjects, but are these what Grandes calls variations. So you take the slice category over the object, so the elements of these posets are just arrows into A. And then the order is given just by the existence of some error. Okay. This is what PO there means poset reflection.
Maybe this is the wrong time to ask, but this raises a question for me. Knowing Lawvere, why did he have the base category post sets rather than small categories?
Oh, right. Yeah, I don't know. I don't have an answer actually. He also considered the that more general version for sure, but maybe only later on.
So maybe it's just because it's less tractable. It's just harder to think about.
Yeah, right. It's also, I mean, a bit more difficult to justify to logicians maybe. But in the end, like part of our current work in progress is to precisely lift the theory of doctrines to digressions.
Yeah.
Okay. So let's look at some more interesting doctrines than just the plain ones. If your posets they have finite means, then you speak of a primary doctrine. This is like a theory with finite conjunctions, and you can go all the way up to first of the logic. If you require the fibers of your doctrine, the posets to be hiding algebras, you want the reindexing to preserve all the structure of a hiding algebra. That was the case also before, I forgot to say. I mean, every time you have some kind of structure inside a poset, inside the posets of your doctrine, you want it to be preserved under reindexing. It's a general principle. The idea is that this preservation means that the substitution commutes with your connectives. And then you want these adjunctions, which are in fact Galois connections because they are between posets. And this PR2 is this guy here, is a projection, product projection. And as I mentioned before, the two adjunction relation here is the one for the existential quantifier. So formally, they mean that the Hom set of this poset here from a formula to the weakening of another formula is in bijection with this other Hom set of the poset. This is telling us that this guy is left adjoint to this other guy. And if we rewrite these Hom sets using the ordered relation, rewrite that ordered relation with entailment, you see that basically this going back and forth, one way gives you the introduction rule for the existential quantifier, and the other direction gives you elimination rule for the existential quantifier. And the same happens for the universal one. Where here I renamed the reindexing along the projection with this WA, which stands for weak. All right. And then we want to also speak about equality, which is quite a central concept in mathematics. And this is captured by the notion of elementary doctrine, where again, equality is introduced by means of a Galois connection. Now we want left adjoint to reindexing along this guy here, which is like a parameterized diagonal. You see the parameter I remains the same, and is the variable in A that gets duplicated. And oh, sorry, I also forgot to say something about this Bakshi-Wally condition before, but we can talk about it now. Now, these left adjoints, they have to satisfy these two rather technical conditions. They may look very technical at first. So the first one is telling us that basically if you index a formula along this diagonal, then somehow you can bring it out of an existential quantifier. And the second one, this Beck-Chevalier condition, is there that was required also for these other two adjoints. Is telling us basically that the substitution commutes in a suitable way with the quantifiers. So if you want to substitute a term into a quantified formula, you substitute a slightly different term that tracks of the additional variables inside the original formula you're quantifying. Okay, but it is. At least usually when people look at this definition first, they are very puzzled. Somehow here one can, with a bit of calculation, see the connection with the usual elimination introduction. Here is really as clear. And this result maybe turn out to be helpful. Is a characterization of when a primary doctrine is elementary. And it's telling us basically that it is so precisely when there is an object like that, which we can think of as an equality predicate. That's why the name. And this predicate needs to be reflexive in the sense that it proves that thing is equal to itself. It needs to be substitutive in the sense that if you want, this is a sort of indiscernibility of identicals in Leibniz sense. If you know that a formula is true on some term and you know that the term is equal to another term, then the formula must be true also on the second term. And finally, you want this equality predicate to interact well with products. So you say that you can prove that two pairs are equal precisely when their components are equal. And now with this characterization, I mean, to go back to the left adjoint from before, one can see that the left adjoint is actually behaving in this way. It's taking this conjunction with the equality, and which is like the domain of the substitutivity thing over there. And now the adjoint relation becomes the equivalence between these two integrals, which looks more like equality.
Jacopo, may I disturb you a minute? I think, I just want to comment that everything that you mentioned till now, it only works for kind of traditional logic. It doesn't cover things like linear logic because, you accepted from the beginning that weakening was part of the thing. And now we also need the diagonals. So then we have real products, right? So
yes.
Yeah.
Yes, thank you.
Thank you. Just confirming my own not understand. I mean,
you're perfectly right. Yes, it doesn't work for linear logic. It only works for intuitionistic logic.
Yeah.
And basically, you need to be able to have weakening and contractions.
Thank you.
Here, you wrote the top. Okay, so you're assuming that every process has a top.
Oh yeah. When I mean finite means, I mean that there is also the anti-means.
Okay.
Okay. Other questions?
Is there any form of compactness to deal with finitary aspect of logic?
Not yet, but it would be interesting to have a formulation.
Then you get logic to it, you get into this Tarskian schema, right?
Oh, of course, yeah. I mean, we don't even have a complete form of the like Gödel's completeness theorem at the moment, actually. But I'll say something later, maybe about that. Okay, so let's look at the previous examples in light of these definitions. So this the syntactic doctrine that we saw before, I mean, it satisfies those enjoys those structures as soon as the underlying logic has connectives and predicates or quantifiers. In particular, if you have you're in intuitionistic logic with equality, then you have an elementary first order doctrine. And for H sets, where we call H was just a poset, to have it have the doctrine elementary, you need a bottom element. This way, you can have a sort of a delta, Kroneker's delta, which because you need to be able to construct function like this that tells you when the two components of a pair are equal or not. Say that they are not, you need to map them to the bottom element. Right. And if your poset is a complete hiding algebra, then you can build also can construct also the allo connections. And particularly this holds for H equals 2. And in the case of the subobject doctrine, well, this doctrine is always elementary. The equality predicate is just a diagonal. Yeah, if you know that your underlying category is hiding category, which is somehow precisely the same thing as saying that the subobject doctrine is first order doctrine. And yeah, I have all the structure we've seen before. And now for weak subobjects, you need in fact something a bit different. It is still elementary because these arrows are still there, but then yeah, the structure that before was required only on subobjects, now it must be required on every arrow. So now you need a locally Cartesian closed category with finite disjoint coproducts. So this means basically that the disjoint coproducts are there to in order to have disjunctions, and locally Cartesian closed means that you have exponentials, and moreover, that not only you have exponentials, but you have exponentials between two objects that live over some other one. And in this way, you can construct implication and universal quantification. Yeah, we'll see that models in these two doctrines are rather different. Okay, so in order to get to models, we need to speak of what a morphism of doctrines is. So this is a pair. I mean, this is the standard notion of a morphism of two posets in category theory. There's no nothing surprising here. So what you need to have is a functor between the base categories that preserves the finite products. So you're sure that the contexts do not get mixed up. And in particular, it also maps terms on one side to terms on the other side. And in the functor, it preserves the sorts and the of the context and the sort of the term. Right, and it must commute, the functoriality means that it must commute with substitution of terms into terms. So it's really, if you want, an interpretation of the language of one doctrine into the language of the other. So this is, you can think of the functor part as the interpretation of the language. And then you also have a natural transformation, this G hat, that goes from one doctrine to the other one, but where you keep track of the fact that you have interpreted the language already. So basically, you map formula in a certain context to a formula in the interpreted context. And again, naturality means that this commutes with substitution.
As far as I understood, context is something that you have when you have the syntactic.
Right. I got a bit. Yeah.
Right.
Yeah. I'm thinking of the objects of the base categories as context. I'm calling them context.
Okay.
But,
So that's a notation that reminds the notation of context that you
Right.
explained before, but it's not exactly that.
yeah. Yeah. So what I should have written in the slide is this one, not what I wrote there. That's more of a syntactic sugar, if you want, or maybe reversed. But yeah, it's just to somehow keep the intuition, the logical intuition, let's say. And of course, the same applies to G hat. So yeah, this is just the notation. What is really happening is this. Okay. Other questions? Otherwise, we look at some examples.
Sorry,
Yeah.
a morphism or doctrine is a model, correct?
Yeah, we can think of it as a model.
So it means that, to say it in a very naive way, a semantic is an association of the two syntaxes.
Of course.
Okay.
Yeah, a priori, there is nothing semantic about R. Definitely.
So model is no more a semantic notion. Yes.
Yeah, I mean, I'm not sure. Maybe there are still some kind of doctrines that are more important than others for these models, and then they be called semantics. But this is to be seen. Yeah.
That I like very much because I detest semantic.
I mean, usually, like here, when people speak of models, they mean morphisms of doctrines into the power set. This coincides with the Tarskian notion of model. Basically, you interpret the formula as suitable subsets of the sets that interpret your sorts. Right, and in particular, if you want a model with equality, then you want to take a morphism of doctrines, which is also elementary, so it preserves the elementary structure. And if you instead go into a subobject doctrine, then in this way you recover the topos theoretic models. For instance, you can take, here I have an example with the effective topos, which I don't know how many of you know it, but it's you can think of it as a universe for recursive mathematics. So basically, it's like having sets and functions, but every function is tracked by a realizer, by a code for a partial recursive function, and so basically all the constructions that you do in this topos, they are partially recursive. And yeah, and a morphism into this kind of subobject doctrine gives rise to what is called a realizability model.
So is that just a term, or is this really realizability as in Kleene realizability?
Yeah. It's I mean, it's structured in a different way. but the idea is precisely the same.
Yeah, okay.
I mean, the point is that on the right hand, when you map a term that you have in your theory to this kind of topos, you're assigning it to one of these functions that already has a realizer.
Yes.
So it's like providing the term with a realizer. And now the weak subobject doctrine. This is, as I said, the less well known, also among people working in categorical logic, in fact. And the nice thing about the models in this kind of doctrine is that you can think of them as a sort of BHK interpretation, sense of Farauer, Heiting, Kolmogorov. Yeah, this was already suggested by Lawvere in his this paper, 90s. It seems that he got this idea by looking at the proof of completeness for intuitionistic logic due to this Swiss mathematician called Leuchli. We used the topos of G sets of actions of a group on sets in order to give a completeness proof for intuitionistic logic. And Lawvere observed that Leuchli seemed to be using not the subobject doctrine on this topos, but this other doctrine. And the point is that in this way, in an interpretation into the weak subobject doctrine, you're able to validate the axiom of choice, like you will do in a BHK interpretation, but you're not validating the low-excluded middle. So in this sense, it's very different from an interpretation into topos using the subobjects, where in that case the axiom of choice would imply the low-excluded middle. And this was observed by Steve Audi, again, already in the 90s, and then was made more precise by Eric Panger in this paper. And I don't know if you're familiar with dependent type theory. There is something called the type theoretic axiom of choice. Which assumes this form. So if for every x there is a y such that, then you can actually find a function from y to x such that this function is giving you witnesses for r, x, y. And in fact, you prove that this is an equivalence in that theory. You can always go the other way around, of course. Basically, this is the reason why the axiom of choice works, because this works in every locally Cartesian closed category. In fact, it's called the distributivity of the products over the sums. Yes. Nothing different than that. And if you take this distributivity and look at it from the perspective of the doctrine of weak subobjects, then you get the axiom of choice. Nothing more than that. Okay. Questions about these examples? So let's get to other kind of level of morphisms in these gadgets. And now if you have two morphisms of doctrines, F and G, the theory of categories tell you that you can consider a two-cell between these two guys, which is a natural transformation between the underlying functors, F bar and G bar, which means that for every object A, you have an arrow in the base category of R, which goes from if you want, the interpretation of one sort to the interpretation of the other sort. And moreover, this natural transformation, or the components of this natural transformation, each theta A, must satisfy this property, which I will explain in a moment. Just to observe that in this way you get a two category, where the objects are doctrines, the morphisms are the morphisms of doctrines, and the two cells are these two cells here. So I mean, two categories, like a category is just that you have an additional level of error that behave in the same way as the level. Okay, but how can we think about these two cells? And here is an idea. So if we think of arrows in the underlying category of some doctrine as terms, then to have a family of arrows is to have a family of terms. From the interpretation of one sort to the interpretation of the same sort in the other model. And the triangle that appears here is telling us that this family of terms, when you substitute them into some formula, well, this substitution preserves the validity of the two interpretations. And in particular, if you take models into the power set doctrine, so the usually model Salatarsky, that means that the base category of your codomain doctrine, the thing you're interpreting in, the base category is the category of sets. So a family of terms in there, family of arrows in that, is just a family of functions from one set that interprets the context A to the other set that interprets the context in the other model. And the triangle becomes this implication, or if you want, you can read it also in this other way. It's just two ways to write down the same thing. And this looks very similar to something that people consider in model theory. And in fact, when the theory is classical, these two morphisms will also reflect validity in the sense that this implication is a bi-implication. And moreover, if your theory also has equality, you are also reflecting the validity of equality, so you can prove that your functions are all injected. And basically, you obtain what in model theory is called an elementary embedding. This is telling us that when you look at a classical theory with equality, the only kind of transformations between the models that you can have are elementary embeddings. And this explains, at least to me, why this is the only notion that appears in model theory. Why there are no other kind of notions of transformations between models. Of course, if you weaken the logic, you work in intuitionistic logic, or if you don't have equality, then somehow this collapse of all these notions of two cells disappear. But they do collapse when you have excluded middle and okay, so here are some of the two categories I've been speaking about, and some additional one. So we on the right hand side we have the two categories of doctrines, and then the two categories of primary doctrines that in particular are doctrines. So there is a so-called forgetful functor, forgetful two functor, going from primary doctrines to doctrines, and then here's useful to have this one. Then you have elementary doctrines that in particular are primary, and this is the subcategory of existential doctrine, which are doctrines equipped with an existential quantifier and not a universal one. So basically,
If you could write with darker marker.
which one is darker?
I think there is a black one.
But that's one. Well, before it didn't work very well.
Ah, sorry.
Is it better?
Sorry.
So these are all forgetful functors that you're picture.
No, these are all okay. So yeah, sorry.
Yeah, no, it's not.
So how is X doc? Wouldn't I have wanted to call those regular doctrines? Existential quantification with conjunction because
Right.
because they're primary.
You want, no, I mean, they in particular, they are primary.
Yeah, and they have existential quantification.
Right.
So this is what regular categories
You missed
classify.
quality.
Okay.
So this you would call regular doctrines. Yes.
Sorry?
This you would call regular doctrines.
Okay.
Because they support the same kind of
Yes.
structure that the regular logic does, or the regular categories have. So that's the
Okay.
fragment with finite means, the existential quantifier and the equality.
Yes.
So
Regular logic.
all of that are doctrines. Okay, so
Two categories of doctrines. So these are collections of doctrines together with their morphisms and their two cells, and they are collected according to the kind of structure that they enjoy. So here you only have finite means. Here you have finite means and equality.
So to say in a trivial way that are sort of doctrine,
Yeah. if you
type
want.
of doctrine,
Yes. Yes. You can think of
species
that
of
way.
doctrine, to
Exactly.
not use terms that are
Categories
other
of doctrine.
category of
There are
doctrine.
two
Two
categories.
categories of doctrines. Yes.
Okay, but then you have a category of doctrine. Under this category of doctrine, there are a lot of doctrine,
Mhm.
and under any doctrine, there is a lot of theories, or one doctrine corresponds to just one theory.
No, one doctrine for one theory.
One doctrine for one theory.
Yeah. I mean,
Well,
you,
well,
you can have,
well,
you can have
well,
different
that-
theories in the regular
No,
logic
I see you change the axiom, you change the
doctrine,
doctrine.
yeah, sure. because the order in the poset will change. Sure. And the formula, the elements of the posets. Also.
So then it's not a theory of theories, it's just a way to describe theories.
Isn't that a theory?
There is a great difference because if to a doctrine correspond to one theory, so you have simply one other way to present the theory. But the theory is one.
But they
This
also
doctrine
correspond
is
to
one.
isomorphic
I presented this theory
No,
with
but
another language.
Isomorphic theories as well.
But I do not. So
I'm
in
not-
order to have a general theory, I go to the two categories because
Yes.
there I have something more a description of a
but
theory.
that's what
Yeah,
this is.
That's what we're doing. Exactly.
Yes.
Okay, good.
Okay, so let's move again a bit more on the left. By CH mean coherent. So this means that you also have disjunction. And then you have the first order ones, where you add also implication and universal quantification. And here below, these two are more propositional. These are the doctrines where you just require the various posets to be hiding algebras, and here you require the fibers to be Boolean algebras, and well, here you also have the quantifiers. these are just some of the doctrines. Sorry, two categories of doctrines that that you might want to consider. There are many more, of course.
Sorry, let me understand.
Yeah.
Now, suppose, let me reason in traditional way, because the only way that I'm able to reason, and then I want to know what is the correspondence. So I have first order predicative calculus. This is one doctrine. And then I can add some axioms and to construct Peano arithmetics. So Peano arithmetics is another doctrine, another doctrine. So what we are doing here is not only for logical theory, it's for mathematical theory. So I mean, adding proper axioms does not modify
maybe I use the term logical in not
adding proper axiom, and so adding vocabulary does not modify essentially the picture. That's what I mean.
Well, but Marco, there's, at least in some of these cases, there are free objects in the other direction. So from doctrine to primary doctrine, there's a free primary doctrine.
Right.
So I see that you do not only translate my English, but also my philosophy now. Thank you very much.
I tried. I tried.
Yeah, that's where we're going.
So when you said first order logic, you meant the theory that has no axioms.
Exactly. First order logic, first order predicative calculus is the theory with some proper action.
But there's another.
Then I add some proper action. I have, for example, Peano arithmetics.
But there's another level at which you could have meant that, which is that you were in the two category FO doc, which is the category in which all of those, the two category in which the simple first order logic with no axioms is there, but so is Peano arithmetic, and so is ZFC, because those are all first order theories. So they all live, the point of this is that that organizes all of them into a two category.
So you means that there is a two category in which both ZFC and the Peano arithmetic belong.
They both live in the same, exactly, because they both have equality, they both have universal.
So independent of which axiom they are.
Right, that's right. So this is a classification system for the language in which you express things.
Okay, but I have also this classification system. I can simply say that both Peano arithmetic and set theory are first order theories with proper axioms. So this distinction I already have in my formal language. Here I have a formal language that allows me to repeat this classification by identifying
but you get more benefit from doing it this way, because now you have this two categories. So you have ways of comparing, as opposed to simply saying they both happen to have the same.
Sorry, I asked something to him, I cannot ask you, because you were not this morning in the discussion.
I see.
But so this, in some sense, is the level of abstract semantics, abstract syntax, if I understand well.
Yeah, I think maybe so.
You cannot understand.
I'll be guarded.
The referral discussion that you had this morning. Okay, go.
Right. So maybe I don't know. I hope this will maybe answer for part of your question. Just to have an example of what we can do with these forgetful functors. You can construct left by adjoints to them, and what it means to have a left by adjoint in this particular case of existential doctrines, for example, you are forgetting, following the red arrows, the existential quantifier, and to have a left adjoint to that means that you're freely adding an existential quantifier. This really means, like in the syntax, adding the quantifier itself. That's a free operation. But this happens at the level of every doctrine, essentially. And I mean, the idea is that in principle, you should be able to have these left by adjoints just by general reasoning similar to Birkhoff theorems for free algebras, because the language is completely algebraic, or I should say essentially algebraic. So in principle, they all exist. The problem is to describe them in a useful way. And in the particular case of the existential, a useful description was given in this paper that actually came out of the thesis of Lawvere. And to unfold a bit what it means to have a left by adjoint in particular, is that you have an equivalence between these two home categories. Now, since the guys above are two categories, you don't have home sets anymore, you have home categories. And the bi-adjunction is telling us that that there is an equivalence between these two categories of morphisms of doctrines, which is telling us that to map out of a free doctrine into some existential doctrine is the same thing as to map out of the original one into the other one, forgetting that it's existential. I mean, this is what happens with free algebras in the usual sense. It's just that here we have one level more. We can relax things a bit more because we have also two cells. So we replace equality with isomorphism. So the bijection becomes an equivalence. But the principle is precisely the same. And from a logical point of view, one can read this equivalence as saying that the extension given by this free construction is conservative, in the sense that it doesn't change the model of the doctrine. And this is a very useful property. And just to give some ideas, now this left by adjoints to this other red forgetful, they are not present in the literature as far as I know, but yeah, shouldn't be too difficult to give explicit description using this FUM construction, which I mean, it happens between categories. But if you apply it fiber-wise, should work for doctrines as well. So what I mean by FUM that you take the two categories with coproducts, and you forget that they have coproducts, and these are finite coproducts. And this FUM in is a left by adjoint.
Okay.
And so this happens in particular. Proposals. The thing restrict here. And now you apply it fiber-wise to the doctrine, and that should give rise to that adjoint delta. And this also works for products because of the opposite operation. So a category with finite products is such if and only if its opposite category has coproduct, or the other way around if you want. Category that has finite coproducts, if and only if its opposite has finite products. And of course, the opposite of a category is a category. Here you have a functor giving you finite coproducts, and in this way, by taking 2 times op. You can also add finite products. In the propositional case, we taking the fixed points of the this double negation should give rise to left adjoint there. Again, working fiber-wise, you apply this this restriction to fixed points to each fiber, and in this way you pass from Heyting algebras to Boolean algebras. Of course, one could wonder how the Gödel-Gensen translation gives rise to a left by adjoint, the forgetful, that is the leftmost, forgetting that your that your doctrine is Boolean. I don't know of any work in that direction, but that would be
interesting.
And now the with left adjoints, the implication and universal quantification are the most problematic, and this happens also at the level of categories, not just doctrines, and that's due basically to the fact that the exponential if you think of it as a functor in y and x, has 2 different variances. So it's covariant in the codomain and it's contravariant in the domain. And this makes it difficult to give an explicit description of left adjoints to the forgetful functor, for example, from Cartesian closed categories. To finite product categories. So these are categories with exponentials that I mentioned before. That is the basic ingredient to get the implication and universal quantification. And it's not clear in general how to construct it. One usually needs to restrict the sub-2 category of this, where you take only isomorphisms. So only the invertible ones, which basically are invariant under this variance. So,
Well, I mean, in domain theory, you can do this by taking embedding projection pairs.
What, sorry?
Embedding projection pairs.
Oh,
So section retracts instead.
oh, that's interesting. I didn't know.
Yeah, that's something that well, Scott figured out, but then it was more elaborated by Peter Fried.
Okay. Then, well, I'm not aware of any
So
application of
it's
this.
it's a way of treating when you want to find fixed points of domain equations involving exponents, then you have this problem of contravariance.
Right.
So if you only consider yourself to be worrying about pairs of morphisms that are maybe even just adjoint, I'm not sure, but the version I know of, it's an embedding projection pair. And that allows you to transfer from being covariant to from contravariant to covariant.
Right.
And still make things work. So that bit of literature might be something.
Yeah, that sounds very interesting. But are you aware of any work that applies to
No,
this?
no, not applying it to this. No, it just sort of I just saw this family resemblance there.
Yeah, no, definitely. It's,
I think Abbas Edlat did lots of work on that.
Yes, that's right. He did.
I didn't catch the name. Sorry.
Abbas Adalat.
Okay.
I'll give you his name.
Thanks. Right. So this is to say that, I mean, in this particular case, for Boolean doctrines, an adjunction was constructed by Marco Badini and Francesco Gufanti. But yeah, it's using Birkhoff theorem for free algebras. So basically, it only works at the one level. So it would be good to have a more general version that applies to 2 categories also. And again, this left adjoint is not explicitly described either. I mean, I guess by working out the proof carefully, one can extract some explicit description, but I'm not sure how nice that is. It's also very recent, this work, so we'll see how that goes. That's all I wanted to say about this diagram. Now, up to now, we've only been speaking about connectives and quantifiers. And here are a few examples of other principles that you might want to consider. The first one was introduced by Emili Maietti and Pino Rosolini. Emili was mainly motivated by working out a rigorous semantics for her minimalist foundation. Basically, the main tool there was the need to freely add quotients. And as it turned out, the same thing happened in several other places in categorical logic, and I will show you some examples later on. The second property that you might want to consider for a doctrine is to have comprehensions. So this means that from the formula, you get a subobject. Which is the extension of that formula. A subobject of the sort of the formula. Another thing you might want to consider is a doctrine with extensional equality. It's because, I don't know if you noticed, but in the definition of the category of context, I didn't take equivalence classes of terms under the provable equality. Because this is not needed in the case of doctrines, even if you have a usual model. If you know that this model is elementary, that it maps the equality on A to the I don't know. This fact is enough to ensure that provably equal terms become mapped to equal functions. And that's because if you have your two terms here on the left-hand side, to have a proof of this basically means that from the top element over B, you can go to the equality. Or if you want your index the equality with respect to these two arrows, it's like you substitute these two terms into the equality predicate. And then to say that this is valid in the fiber over B is to say that you have an arrow from top. And now this arrow here, let's say that these are a model. This is the interpretation of your two terms, which are actual functions paired together. And this arrow, because the top element gets mapped to the identity, tells us that this square must commute, which ensure the fact that these two functions are actually equal. So this is why you don't need to quotient out the terms under provable equality. But you still might want to do that in some occasions. And this is especially useful if you want to establish a connection, for example, between elementary doctrines and algebraic theories. Because one would be tempted to take, if you have a doctrine on C, like this, then one would like to think of the underlying category as an algebraic theory. But the problem is that we need to incorporate the equality of the doctrine that lives here into the category. And this is done precisely forcing the equality of arrows to be the provable equality of the doctrine. So basically what to have here you have a forgetful. And here you have the underlying functor that now goes into algebraic theories. And here, Maietti and Rosolini describe this left adjoint that basically allow you to see elementary doctrines as a way to speak about algebraic theories. Well, actually, yes, they described left adjoints to all those forgetful functors that you see above. Now, if you combine all these adjoints that I mentioned, those by Maietti, Rosolini, and also those from the slide before, I mean, this is basically all work done by Maietti and Rosolini. You recover various constructions in categorical logic and also in the semantics of type theory, because motivation is needed, as I said. So I don't know how familiar you are with these constructions, but they are very, very well known and very much studied in categorical logic. The exact completion is as I said, adding quotients to a regular categories or to a category with finite limits. The pre-topos completion was introduced by Mackay and Reyes and allowed Mackay to prove his result known as conceptual completeness. So the pre-topos is basically are those coherent categories that basically are equivalent to their categories of models. So you can recover a pre-topos from its models, but if you start from a coherent category and you look at the models, then you recover the pre-topos completion of the coherent category. And then the tripos to topos is a very important construction that was introduced by Hyland, Jostman, and Pitz, with the motivation of giving a way to construct the effective topos. And it turned out to actually construct a lot of interesting toposes, including all realizability toposes and also shapes on our cloud. And well, it can also be weakened to other contexts, but let's not have too much into that. The last one is a bit different. A setoid model in type theory is used to interpret an extensional theory into extensional type theory into an intentional one. And the reason we want to do that is basically that the extensional type theory is a very nice place where to do mathematics. It enjoys the usual properties of the theory is everything is just a bit more structured, but basically the terms there behave like functions. The problem with extensional type theories is that they are very badly behaved from a computational point of view, while the intentional theories they behave much better from a computational point of view. It's much easier to give normalization proofs for them. So these setoid models tell you basically that your extensional theory is conservative over the intentional one. Usually they are constructed by hand, but this quotient completion by Maeta and Rosolini is a way to obtain them more easily. Right. So as I said, in all these examples, a central role is played by the left by adjoint to the forgetful from doctrines with quotients to elementary doctrines. And so let's look at it a bit more closely. So the forgetful that I mentioned before and its left by adjoint appear here. And now I will explain the rest of the diagram. So first of all, Fabio Pasquali noticed that the construction of this quotient completion didn't really rely on the hypothesis of having an elementary doctrine. It's enough to have a primary one, just the conjunctions. And if you perform the construction in that way, you get a right by adjoint to the forgetful functor. And it was later proved by Davide in his thesis that this by adjunction here is monadic in the sense that this comparison functor from doctrines with quotients to algebras of this two monad, it's always an equivalence. So the fact is that this by adjunction, like any by adjunction, gives rise to two monad on this category, monad called T prime, and every two monad give rise to another by adjunction with the category of algebras, where this left adjoint is the one picking out the free algebras. And well, it's very well known in category theory that this kind of by adjunction is the terminal one among those that give rise to this two monad. And this means that you have this canonical comparison, which in general is not an equivalence, but in this case it is. And moreover, he also proved that this two monad is lax idempotent, which is a technical way to say that basically two algebra structure on the same doctrine, they must be isomorphic. And this is very reasonable if you think that you want to characterize something which enjoys a universal property. It's the same with finite products. If you have two products of the same two objects, they must be isomorphic.
Jacopo, can I stop you again? I wanted to kind of trying to understand where the comprehension fits into this picture, because I can see that half of what you're talking about now is the existential completion that David did, and the other half is the coalgebra thing that Pasquale did, right?
Yeah, there are no comprehensions here. So they appear here.
Right.
For the pre-topos completion, for example, or the tripos to topos also. But not in all these examples.
I see.
In particular, here I'm just focusing on the quotient completion.
Fantastic. One more question on that. What is the reference for Thomas Erhard stuff on that, on the comprehensions again?
I don't have the name of the paper on top of my head.
Okay.
It has vibrations and type theory in the title, I seem to remember, but I can send you the reference later.
That's fantastic. Thank you so much. And sorry to disturb you in the middle of the flow.
Right, we were saying about the result by Davide. When you have a property characterized by, when you have a structure characterized by a universal property, then this must be unique up to isomorphism. This is the categorification of what you have when, I don't know, if you take a mid semilattice, then you know that the meet of two elements is unique. Here it's the same, it's just that it's unique up to isomorphism, because you move from a poset to a category. And the reason it holds in this case is that quotients are given by a universal property as well. So they are unique up to isomorphism. And so this is what it means to be Log-side important. And finally, this is when I joined the party. It was in 2019, but then the paper got published in 2020. We proved that also on the right-hand side, well, now the things are a bit different because you see here you have left, right, so you get a two-monad. Here you have right, left, so you get a co-monad instead on primary doctrines. So you look at its co-algebras, and again, you have a canonical comparison, which we proved to be an equivalence. And we also proved an analogous result saying that the comonad is also Log-side important. Again, because if you recall, equality was also characterized by a universal property, being a Galois connection. And in that paper, we also applied that construction to a construction in model theory that was introduced by Scheler in his work in classification theory, where he proved the Morley's conjecture. So there he constructed this theory T-Eck. There is an extension of the theory T with the property that it has, basically it has quotients of definable equivalence relations, but it enjoys the same models, which is a conservativity result. So it's natural to try to express that categorically using an adjunction. And so there were also other formulations of this result in categorical logic. One was suggested by Mackay and involved the use of the pre-topos completion that was worked out by Harnik. But yeah, it turned out that we need much less than the pre-topos completion to do the same. Anyway, this fact of having quotients of definable equivalence relations in model theory is expressed by saying that your theory has uniform elimination of imaginary elements. The imaginary elements in question are the equivalence classes that you want to consider for your quotients, that are imaginary because they are not there, but somehow you add them freely. And yeah, it turned out to be a very important property for theories in model theory. And using the comonadicity and the Log-side impotency of elementary doctrines over primary ones, we could prove that the right adjoint described by Pasquali gives rise to a theory that, in the sense of doctrines, that eliminates imaginary elements. And moreover, whenever P is elementary, so whenever your theory has equality, you get an embedding which gives rise to an equivalence between the category of models. So this is how you get the conservativity of Scheler's construction. And so the main difference is that this is much more general in the sense that it does not necessarily apply only to complete theories in first order classical logic, but or any primary doctrine or any elementary doctrine according to the property you want to derive. So this is my last slide, which is some of the things I'm currently working on, at least along this line of research. So as I mentioned before, my main focus now is to try to lift this theory of doctrines to the case of grothendieck vibrations, which you can think of as indexed categories. So you drop the requirement that between two proofs, between two formulas, there is only one proof, and instead you allow the fact that there might be more than one proof that from alpha give you beta. So this is something called proof relevance. And it is the main difference between type theories and what I've been calling logical theories. Right. And so in this case, with Fabio and Pino, we were able to obtain the same characterization for vibrations with equality that I presented at the beginning of the talk in terms of an equality predicate. What happens now is that the equality predicate becomes a groupoid. So the structure of groupoid and groupoid actions become central in order to describe this proof-relevant notion of equality. And this is very much in line with what is known in dependent type theory, where actually the first model that didn't collapse the equality predicate in type theory to a proof-relevant thing was a model in the category of groupoids, given by Martin Hoffman and Thomas Streicher. Right, another thing that came out of that work that I'm working on currently is to apply this characterization in terms of groupoids to descent theory. And so that was a theory developed by Grothendieck that basically is it gives you some tools in order to understand when you can let some kind of structure descend along some morphism. Most typically, you want to consider a quotient function, and you know that the objects of your domain of the quotient enjoy some property or even some structure. Typically, you have a sheaf over your domain, and you want to understand how to carry these properties or this sheaf to the codomain. And this is what the descent theory allows you to do. Yeah, so what I got for now is a proof of this theorem by Benabou and Robot, which gives sufficient conditions for this kind of descent to happen. But yeah, I would like to investigate more of that. Then, together with Francesco Dagnino at the University of Genova, we had a master student that just defended his thesis, where basically he gave a version of the completion under comprehensions for Grothendieck vibrations instead of doctrines. And then those kind of comprehensions are those that basically characterize the Grothendieck vibrations that give rise to models of dependent type theory. So it would be nice eventually to use all these tools to unify the semantics of dependent type theories and first of the logic. But yeah, I'm not sure how far there is. Anyway, we're slowly moving towards that direction. And finally, another thing I'm working on together with Ivan Di Liberti and Joshua Reigli is to relate the completions that already exist on categories, like the classical categorical logic in terms of categories, to this kind of categorical logics in doctrines and their completions. But of course, there is work also of many others, including Jonathan here and Valeria, who's listening remotely. Especially in the case of Grothendieck vibrations, actually. But yeah, I think that's all I wanted to say.
We have some time for questions.
I have one question. You mentioned the fiber. They are endowed with, say, minimal time algebra, right? And that excludes many logics that not algebraizable by this kind of logic. You could probably add some more complex stuff like big block algebras or any other kind of.
Very ignorant.
Would be a very nice way to expand that.
Absolutely, yes. In fact, I mean, there is a lot of work that needs to be done with this framework, both in terms of the kind of thing you can do with the tools that I mentioned, but also in the sense of expanding the definitions in order to allow for more general examples.
Right. Sort of strict.
Yeah. Like also, I mean, this is also related to Valeria's comment that since we are assuming that you have finite products in the base, we have no hope to capture linear logic.
Yeah.
We should replace that product with a monoidal product, and who knows what else needs to be changed. But yeah, I mean, this is certainly nice work to be done.
Can I say something? I just want to say thank you very much because it was a great talk. I understood lots of things that I hadn't understood before. And I'm sorry that I got it slightly wrong at the end, thinking that was Pasquale's PhD, but it's your joint work with him and Rosolini that I kind of, the equivalence, right?
Oh, the equivalence, yes.
Yeah, it's your, all the three of you on doing that, right? Yeah, I think that's kind of, this whole line of work is very interesting. And as you said, John and I are working on that in a slightly different direction because we want to think about the doctrines that kind of correspond to doing both completion on the co-products and on the products. So to kind of get to something like dialectica, right?
Well, it's iterated. It's not, well, I mean, so at once.
Yeah,
so
exactly.
That's a great question. You know, so that would also be interesting. So there would be the like extensive completion, but dialectica, that's the sigma pi. So
yeah, that's very interesting.
Yeah, that's the question. Thank you, John.
Other questions? So I have a very simple question. So
that is the most difficult. The simple question are by far the most difficult one.
The answer is going to be very, very straightforward. So I'm thinking about, let's say, to put a concrete example, Boolean algebras. And then I think, okay, my Boolean algebras, I want to have the language that consists of negation and meets. And then I know that I can write the axioms of Boolean algebras using only this language. And then using this language, I set up my context, my Lindenbaum-Tarski fibers and everything. And then I set up my category of syntax, the category of syntax for this theory of Boolean algebras with these axioms in this language. And now I do the same with a different language, with a language that has negation and implication.
Mhm.
I construct my category of syntax. What's it called? The category of
Context.
the category of
Or the syntactic doctrine.
the static doctrine. Okay.
Mhm.
What is the relation between the two?
So if I understood correctly, you're asking whether if I add something at the syntax or if I apply the corresponding completion at the level of doctrines.
So I have two different doctrines. One is the one that I construct with the theory of Boolean algebra as expressed in the language with
So if-
negation and MIT, and the other with expressed in a different
If I understand well,
there are different things, right?
Yeah, but they should be equivalent.
They are equivalent.
Yeah.
so there are
So
two
in the-
doctrines.
Because
that
the
are
fact that the rest of the structure is internally definable
Yes.
should hold true in the doctrine itself.
Okay, so in the classical study in algebraic logic, we would relate them by saying that both the varieties are term equivalent,
Mhm.
right? So I suppose that if you have term equivalent theories or term equivalent varieties, then this should be
You get equivalent doctrines.
equivalent doctrines.
Yes.
Do you have more things that are equivalent, but they are not necessarily term equivalent?
That I don't know, but it's a great question. I'm not sure how far the two concepts are. But it's, I mean, actually, yes. Also the connection with universal algebra is something that needs to be explored. It's unfortunately it's not a topic I'm very familiar with, but it would be great.
Seems like the answer should be that there are equivalent things that are not term equivalent.
That's my intuition. There should
One would
be-
think.
You should have more
But
equivalent.
so it would be nice to have examples at hand.
So I think if you take the field on three elements, it will have the same logical theory as the Boolean algebra on two elements, or the ring, I guess I should say. Because they're categorically equivalent, the two theories that get generated by these finite algebras, but they're not term equivalent because term equivalence has to be on the same base set, or at least the same cardinality. So that can happen, I think.
So more in general, what you're asking, if I understand well, what happens when we have formally the same theory with different signatures?
Yeah, with different signatures, yes.
The theory is the same, but we are changing the signature. In this case, you say you have two different doctrines,
No.
but they are equivalent.
Yeah, well, I mean, being equivalent is like having the same doctrine.
For a category theory.
They are invariant under all the two constructions, the two functors that I mentioned. That's what we can see.
And if I have two theories with the same signature and different actions, also.
Well, I mean, if the axioms are interderivable, the doctrines will turn out to be equivalent.
I have a very naive question because this was all very fascinating and wonderful. But Bill's original work in his dissertation was at the level of Lawvere theories.
Right.
And then he modified it to have doctrines. But surely the Lawvere theory story just lifts to the doctrine setting. And how does that work? What do I do if I want to take a Lawvere theory and think of it as a doctrine?
You take elementary doctrines. So, I mean, there's not been done any specific work about this yet. But I believe that somehow the two treatments will be equivalent one to the other. And I hope that this work, we joint work with Diliberti and Reigli, will give us some answers to this.
I'm surprised because I thought it would be a very simple way of just extend. I mean, isn't there a special doctrine that somehow I
I mean,
something trivial to make a Lawvere theory into a doctrine? Because the concept of doctrine was supposed to elaborate this, to capture more.
Yeah, I guess if you take the subobject doctrine of a Lawvere theory, that should give rise to the relevant notion of doctrine of elementary doctrines here. So it will be an elementary doctrine with extensional equality. So you learn here.
Yes.
In this sense, I'm not sure how these two would match precisely because there is an adjunction here and not an equivalence. But yeah, it would be nice to see how far the two are. I think they are not that far.
No. Yeah. All right. Thank you.
Other questions?
Over dinner.
Okay, yes. Thank you so much.
Many thanks to Jacopo. Bye-bye.
Bye-bye.
Bye, Valeria.
1, 2, 3.
Bye, Valeria.
And if I remember well, but I thought it can be wrong, you did not send me the composition of your committee.
Thank you so much.
I signed it also.
Great questions.